All right, so we've done long division, we've done synthetic division, so kind of part of the point behind it, these two theorems we're going to look at. Theorem is just a rule that can be proven. You probably haven't seen this in geometry, that word, but the reason we do this division, one of the reasons is this remainder theorem. And it says, so a polynomial f of x, so any old polynomial, when it's divided by something in this form, x minus c. The remainder is f of c. So if you remember back when we did function notation, if I said f of x was, say, x squared plus 5x minus 9, a fairly simple polynomial. It says if we divide this, so our plan is to take this polynomial and divide it by, let's say, x minus 3. What this is actually telling us, the remainder theorem says, I could use this division and maybe use synthetic or long division, and whatever the remainder is, remainder equals something. Whatever the remainder is, if I had plugged in this c value, so in this case the c value equals positive 3, if I had plugged 3 into that function initially, that would be the same thing as the remainder I ended up with. So is the remainder from the division, or if I had plugged in 3 to the equation in the beginning, we'd end up with the exact same number. That's what the remainder theorem tells me. It kind of gives me a use for that remainder. So what this is basically saying is we can use synthetic division to give us the value of a function. When I plug in a certain number, when I plug in c, I can use that remainder to figure out what that value is. So let's look at an actual example of this. So if we use synthetic division, this is my c value. So in other words, I can take the synthetic division, use -4, because my c value is what we put in this box here. Take my coefficients, 3, 4, -5, and +3. If I perform synthetic division, so bringing the 3 down, multiplying diagonally, adding, becomes -8, multiplying diagonally, add, moving down, multiply diagonally, and that's -108. My remainder here, -105. So my final answer, 3x squared minus 8x plus 27. My remainder, 105. If I had taken that original function, f of -4, and plugged in -4 everywhere I see x, I would get out the exact same value as my remainder. So just a different way to kind of get to the exact same information. You can type that into your calculator and verify, but it should equal to -105. So synthetic division just gives you kind of a different route, a way to get to an answer that maybe would appeal to some people as being a little bit easier. So remainder theorem gives you a use for that remainder. What about, so the difference then kind of comes up, well, what about when there's a remainder versus no remainder? So we divide this first set of polynomials, this first polynomial divides, and there's no remainder. This second polynomial divides, and we're left with a remainder. What does that actually tell us? And so the factor theorem is kind of the other side of this. What can we use the remainder for? Well, there was one purpose. That's what the remainder theorem gives us. But what if there is no remainder? The factor theorem says if you've got no remainder, then that means you found a factor of the polynomial. So for instance, this first one, x squared plus 10, and that should be an x, 10x plus 21, what that's saying is you've actually just factored that original polynomial. It's actually x plus 3, what you divided by, times x plus 7, so what's left over. So if you can't factor, but you know one of the factors, it gives you the power to kind of test out and see if you found an actual factor. So for instance, it kind of opens up this possibility, and we'll explore this more into the next section. But if we know 3 is a 0. In other words, if 3 is a 0, you think, what would that factor had to have been? It had to have been x minus 3. In other words, when we divide this polynomial, 2x cubed minus 3x squared minus 11x plus 6, when we divide that by x minus 3, that's a factor. There will be no remainder. So divides f of x evenly because it is a 0, because it's a factor. So we can use this to help us find other zeros. So if we take our polynomial and perform synthetic division, we are expecting, because this was a 0, because this was a root, it's a factor. So we're set up for our synthetic division here. Bring down the 2, multiply, add negative 3 and 6, multiply, add negative 11 and 9, and then multiply to get negative 6. So we see our remainder is 0. It says, well, the question is, though, so we've verified that 3 is a root. It says to find the other zeros. So what we're left with here is 2x squared plus 3x minus 2. What we've kind of given ourselves the power to do now is we can find the other roots. We can find the other zeros through factoring or through the quadratic formula. Now that we have a degree 2 polynomial, we can use other methods that we've used before. So, for instance, if we factored this one, go through the factoring, 2 times negative 2 is negative 4. Factors of 4 that add to 3 would be negative 1 and 4. So if we take this middle term and break it apart, minus 1x plus 4x minus 2. So we can factor the ways we've used previously when we were talking about just quadratics to get us to the place. So finish our factoring off, take out our GCF in each group, and we use a method that we're familiar with in order to find the other zeros, to find the other roots. So the idea here is we can take synthetic division. If we can find a factor of something that otherwise we wouldn't have been able to factor, and even if you had grouped this original polynomial, you wouldn't have been able to factor, we take something we wouldn't have originally been able to use, and now we can find our roots. So x is negative 2, and x is 1/2. So our roots in this case, 3, negative 2, and 1/2, just, it gives you the power. We have a way that we can take a third degree polynomial, turn it into a second degree polynomial that we can do a lot more with. So once you have a second degree polynomial, factor, quadratic formula, we have ways that we can deal with those. And that should be it.